All right. Sorry that my copy is kind of light, but I'm going to show you Hess's law. And Hess's law has to do with if there isn't just one single equation that represents a chemical reaction, so that we can't measure it, we can't look up the values in the appendix, take the sum of the products minus the sum of the reactants, but instead we have to relate enthalpy changes to equations that we know. So it may involve taking 2, 3, or 4 equations and combining them in such a way that we can come up with a total enthalpy change. So Hess's law states that the heat of a reaction is constant, whether the reaction is carried out directly in one step or indirectly through a number of steps. And so sometimes when we're combining equations to use Hess's law, sometimes we have to flip the equation around. Sometimes we have to multiply by a coefficient to make, and I'll just show you through some examples what I mean by this, how it all works out. It says here the chief use of Hess's law is to calculate the enthalpy change for a reaction for which such data cannot be determined experimentally or otherwise unavailable. And so we can do it by manipulating equations, and I think showing you by example will be the best way to do that. There's some rules here we'll refer back to as we try a couple problems. So the first thing you want to notice about a Hess's law problem is that there is an equation, a target equation I'm going to call it. There's a single equation that we want to get by combining 2, 3, 4 other equations. In the case of this problem, we have 2 equations that we are going to combine to come up with this one that I'm going to call my target equation. And this is a weird one because it actually gave us the answer, so we can check our answer, see if we got it right. I don't think that's usually the case. So I'm going to look for something on the left side of my target equation, and I see carbon as a solid. Pay very close attention to the state, solid, liquid, gas, because they can mess you up sometimes. And so I look in my steps for a carbon that's a solid on one side of the equation or the other, and I find it here. So these two match up. So if I leave this equation as is, I can get the carbon as a solid in the target equation. Okay, so I don't have to flip it around or anything. I can leave it just like it is. So what I did is I rewrote it down here. Don't worry about the cross through this part yet. By the way, however many steps they give you, you have to use all the equations. So if you ever think, well, I don't think I need that equation, I'll leave it out, you'll have to always use all of them. Okay, then I notice that there's a CO2 over here on the right side of my target equation. So I underline it, and I notice in this second step, by the way, you'll only use the steps once each. You won't use them multiple times. I notice that there's a CO2 here on the right, so I'm lucky in that I don't have to flip it around. I don't have to multiply by anything because these two match up. And so then I write that equation, CO as a gas plus 1/2 O2 as a gas, and that gives me CO2 as a gas. Notice that I carried along the enthalpy values. Sorry, that kind of got cut off. That's a negative 110.5, and this is a negative 283. What I'm going to be able to do to come up with my total enthalpy in kilojoules per mole of reaction is I can just add these. What if I had like 4 numbers, 4 equations? I would just add them up. And so when I add them up, I get a negative 393. Well, then I also want to prove that by combining these 2 steps, I can come up with my target equation. So be careful here. Anything that appears on one side of one equation and the opposite side of another equation, I can cancel them out. And so I can cancel out each one of those. The CO as a gas. I can combine, if they're on the same side, if they're both on the left side of their equations or both on the right side of their equations and they're the same thing, I can combine them. So 1/2 plus 1/2 would give me 1O2. Well, usually we don't put the ones in for coefficients. And so what I have left after I've combined the O2 and crossed off the CO, I write it down. I have carbon as a solid, I have 1 oxygen, O2, and I have CO2. So now my equation matches my target equation. And the point of this problem was to get the enthalpy change, standard enthalpy change. And so for this equation, it's negative 393.5. Well, we got by pretty easily on this one. We didn't have to do a whole lot. We just had to combine them. But what about one like you'll find on the back of that page? Sorry, it's just a bad copy. So this is my target equation. This time they didn't tell me what the answer was, so I won't be able to check it. And I see here that I have 2 carbon in the form of graphite. Well, here I have carbon. These are my 3 equations, step 1, step 2, step 3. Here I have carbon in its graphite form, but there's only one of them. And so to use this equation, I have to multiply everything, every coefficient by 2, as well as my enthalpy change, which is negative 393.5. So I go down here and I multiply carbon as graphite by 2, I multiply the O2 by 2, I multiply CO2 by 2, and I multiply the negative 393.5 times 2. So I can do that as long as everything gets multiplied by 2. Sometimes if it doesn't matter, why am I skipping the H2? I don't know. Sometimes when you get into H2s and O2s, sometimes they appear in multiple equations. So I'm going to look for things that are unique. And I see the C2H4 on the right side. Well, the second step has C2H4 on the left side. So what I have to do is flip the reactants and products. So I flip them and I start by writing this down. 2CO2 as a gas plus 2H2O as a liquid is going to give me C2H4 as a gas and 3O2. Now be careful, because when you flip the equation, you actually end up changing the sign on the enthalpy. So because I flipped it, I have to make this a positive 1,410.9 kilojoules. So I've used the first 2 steps. I have to use all 3. And so, well, how in the world am I going to use them? Well, I notice just with these 2 steps, before I write the third one, I can cross off the CO2. I'm going to probably be able to cross off some of the O2s, but what about water? Does my target equation have H2O in it? No. I need to get rid of the water in the second step. And the only way I can do that is by having water, because this is on the left side, by having water on the right side. And so, well, water is already on the right side. All I'm going to have to do is multiply it by 2. It's kind of like a puzzle. I'm going to multiply H2 times 2, 1/2 O2 times 2, which would just be 1, and 2 times 2H2O. Because I multiplied everything in this equation by 2, I have to multiply the negative 285.8 times 2. So I'm going to keep a running total here. I'm going to add this to this to this to get my total enthalpy. But I want to prove that my equation now matches my target equation. So I can cancel out the CO2, because CO2 is on the right side in one equation, the left side in another. Notice if I add the O2s together, I get 2 plus 1. I have 3 O2s on the left sides, and I have a 3O2 there, so I can get rid of all the oxygen. I can cancel out the 2H2O as a liquid. Be careful, like I said, sometimes it might be the same formula but a different state. It has to be identical. It's not the case in this one. I can get rid of the 2H2O. I think once I've gotten rid of all of that, if I write down what I have left, this 2 carbon as a graphite plus 2H2 as a gas gives you C2H4 as a gas. Does it match my target equation? Yep. If I add all of this together, add negative 393.5 times 2 plus 1410.9, plus 2 times negative 285.8, I get a 52.3. My label will be kilojoules per mole of reaction, just like other enthalpy values that we found. Okay, so that showed us something a little bit different. I can go back and see how I've applied the rules. The rules say when you reverse an equation, the sign of delta H must be reversed. If all the coefficients are multiplied or divided by the same factor, then the value of the enthalpy must also be multiplied. So we've been using the rules. I would like to show you one more. Maybe, I don't know if it'll show us anything different or not. In this case, this is my target equation, and I'm going to combine these 2 to come up with it. So again, I see carbon in its graphite form in my target equation with a 2 in front of it. So everything in this equation is going to get multiplied by 2, kind of like we did in the other problem. I see that I need a 2CO on the right side. Well, 2CO is on the left, so I have to flip the entire equation, write it backwards. So that gives me 2CO2 on the left side, gives me 2CO plus O2 gas on the right side. Because I flipped it, I have to change the sign on the negative 566, so it's actually positive 566. I cancel out the CO2. One of the oxygens will cancel, so I'm left with an oxygen here on the left side. So if I write them down, 2 carbon is graphite plus O2 gives me 2CO. I'll add this value. I had to multiply it by 2. This is a positive 566. I add those together, and it should get a negative 221 kilojoules per mole of reaction. I hope this is enough examples. If it's still not really making sense, maybe try Khan Academy. Or if you have other tutorial sites that you've found that you like to go to, give them a try. But I sure hope that this is going to work for you. There's a worksheet that you're going to work some of these problems on, and you'll find that right below this video assignment.